It's now my great pleasure to ask, Dr. Alan Scott to join us, to take the podium. In fact, here, Dr. Scott, or Alan as he likes to be introduced, is an engineering fellow with the optics group at Honeywell, not the thermostat group. This is the people, and I didn't know this, so I'm maybe the only Luddite in the crowd, but Honeywell is a massive global multinational corporation with, they got a whole aerospace division, they've got a manufacturing division, et cetera, et cetera. But they have also chosen to place their, what they call their space greenhouse, that's their term for an incubator, right here in Canada. And Alan is going to walk us through what that's all about, and I'm personally looking very much forward to hearing about it. Alan Scott.
Okay, just bear with me while I find my slides. All right. So thank you all for coming this evening. I'm really impressed with the turnout. I'm going to apologize in advance if my voice kicks out because I'm fighting a pernicious cold. But luckily we have a microphone, so I can just sidle right up to this and give you my gravelly FM radio voice for the evening. So, I'm an engineering fellow in optical technologies at Honeywell here in Canada. We have a space greenhouse, which was discussed by Steve, which is basically an incubator for space products, for optical space products mainly. Our group here has a long heritage in optical instruments and optical technology for space, which is probably a little known secret that a lot of people don't know, that Ottawa, Canada holds one of the world's leaders in space optics. So that it's a relatively small group, but we're growing, and we're doing some interesting R&D, developing products for Honeywell in communications. And you can see by the title of the talk, I'm going to be talking about optical intersatellite links, a revolution in satellite communications, and disruptive technologies that and impacts of this. So before I get started, I'd just like to introduce myself a little more. I'm a geek from way back before being a geek was fashionable. Who recognizes this? Who's watched this show? Anyone? Show of hands? Okay, yeah. Good. So it's fashionable now to be a bit of a geek, so I kind of see myself in some of these people. So when I did my graduate work in University of Waterloo, I was working in laboratory astrophysics. So I was a bit of a cross between Raj and Howard there, or not Howard, Leonard, doing lasers and physics and spectroscopy and optics and all sorts of cool stuff, looking at the properties of interstellar dust. And then I graduated and got hired in space industry, so now I'm Howard Waldowitz. That's the tight pants. But another little known fact is that some of you who might read comic books might recognize Sheldon's shirt there. That's the Green Lantern, and the actual original Green Lantern is Alan Scott. So Honeywell is a very big multinational corporation headquartered in the US. So wow, 40 billion in sales. This is a little bit dated in 2014. Our group here in Ottawa was purchased by Honeywell back in 2016, early 2016. We were previously ComDev, which was an Ontario space manufacturing company. In fact, ComDev's bread and butter is RF communications payload products. 80% of the world's communications satellites have ComDev parts in them doing RF telecommunications work. There's switches, there's multiplexers, and there's arrays of these things. World leader in volume production. So ComDev's raison d'etre, we have a big factory down in Cambridge where we have clean rooms and high-tech equipment and test equipment and procedures in place that we can reliably build these things and have them operate in space for 15 years with no failures, which is what you have to do. So the PA and the quality assurance to do this is a big factor, and the fact that we can do this and be competitive across the globe in such a manner that we're getting 80% of all the satellites is quite an accomplishment. So this is just a picture of the production floor in Cambridge. Now, our group here in Ottawa has a rather storied past. We originally were CAL Corporation, if any of you remember that from way back, Canadian Astronautics Limited. So I was actually hired by CAL, but when I started work, by the time I started work, it was EMS Technologies. So I didn't get to actually have I think I had CAL business cards for like 1 year. So then we were EMS, and we were the EMS space division. We were building space science, optical instruments, and then EMS was purchased by ComDev, the space division, and the SATCOM division was purchased by Honeywell. And then Roots Astro Engineering was another local space hardware company, which was also purchased by ComDev several years later. And then ComDev was purchased by Honeywell, and we're all back in one big happy family. And you may wonder why so much of Canadian optical space science heritage came to reside in ComDev and now is in Honeywell. And you may wonder why there's been so much consolidation in the space science and space optics. Well, this slide tells a story about world government civil space programs. And you can see in a per capita basis, we're less than 1% of the US, and this is in millions. So the Canadian space market is small, it's hungry, and it's innovative, and it's competitive. The US companies are relatively risk adverse. They have a big gravy train that they're riding from defense spending in space, and they don't want to damage that. So we have a very good competitive position here in Canada, even though we're small. But we can't depend on the civil budget to help us very much. We have to be competitive commercially to survive. And euphemistically, Canadian space companies punch above their weight class. So space science, I just want to give you a little bit of a heritage from our group here in Ottawa and Cambridge as well, ComDev, Roots, CAL, EMS. So here's kind of a timeline since we started building space hardware back in the 80s up to the present. You can see there's various interesting little names there probably many of you wouldn't recognize. Windy was an optical interferometer for measuring winds using Doppler shifts. There was space station hardware. There's star trackers. There's Japanese. There's ESA. There's NASA. There's all sorts of different collaborations here. And I want to touch on some of these in a little bit more detail, just to give you an idea and a flavor for the unknown things that we were doing here, or little known things. Canada's more than just space arms in space. So now I'm going to give you a biased history because it's going to be around what we've been doing here in Ottawa. There are other space companies doing optics in Canada. There's some in Quebec. There's some out in BC. But this is kind of a local Ottawa flavor that I want to give you. So we started out building ultraviolet imagers for looking at the aurora from space in the far ultraviolet. And so here are some of the images from our early hardware. We developed some of this in collaboration with the University of Calgary, and it's been on several different spacecraft. And you can see a picture of one of the instruments from the Freya mission. It's a carbon wound composite tube, inverse Cassegrain telescope, for those of you who know optics a little bit. So it's a wide field, and it's supposed to be athermal. We don't get much feedback after these things launch, but we hear years later that they always wondered why the images of the stars were donuts. So apparently it wasn't exactly athermal. But for a big blurry thing like an auroral oval, it didn't matter. So the future ones actually had heaters on them to keep them athermal, and now they work very well in space. And you can see the bottom right is a NASA image mission, which is taking views of the aurora, auroral oval. Windy was led by Professor Gordon Shepherd out of York University. It's looking at wind velocities in clear air in the upper thermosphere and upper atmosphere on NASA UR's Earth observing mission. It operated flawlessly for more than a decade, and the data is contributed to climate models. And so this was built in Ottawa here by CAL and by Interoptics, which is an optical company here. And then the Michelson there is in the middle, and the filter wheel on the bottom there was built by ComDev in Cambridge. Another interesting Earth observation mission is the MOPIT, a measurement of pollution in the troposphere spectrometer, which is led by Jim Drummond out of University of Toronto. This is a correlation spectrometer, so it's looking at different pollution gases in the lower atmosphere, and it actually has a cell of the gas in with it that it blinks between looking through the cell and looking through an empty cell, and there's an infrared detector in there that measures the difference between the two paths, and then provides a global map of carbon monoxide, which is an indicator of biomass burning, for example. And you can see that it's over the rainforests where they're burning, and you can look at this over the years cycle and see and track these things. And this has been flying on NASA's Terra satellite since 1999. It's still operational, and it has like a gimbaled mechanism. It's like a single point that's scanned back and forth. And this thing has been operating continuously since 1999 and is still functional now. These are a couple instruments. One is the Odin instrument on the upper right. It was built by Roots Astro Engineering here in Ottawa. The bottom left is the Maestro instrument, which was developed with Meteorological Services of Canada, and these are spectrometers that can look at various different gases in the atmosphere in the ultraviolet and the blue region, and the biggest interest is the imaging of ozone and monitoring the ozone hole and its recovery after the Montreal Protocol. So the data from these spacecraft are very important for that sort of thing. Now this isn't really a space science mission, this is an optical star tracker. A star tracker is basically a star camera that goes in satellites and autonomously decides where you're pointing. You can get these apps on your phone now, but back then it was really cool to be able to do this. So it would point to some stars and would tell the satellite which way it's pointing, and the satellite would then reorient itself so that it would be stable and point the direction it wanted to. And you can see this was developed here. It was one of the world's first autonomous star trackers. It was developed here in Ottawa and tested out at the Fred Lossing Observatory, which is part of the Royal Astronomical Society's property. In night sky tests, we used to take them out there and test them before we fly them on the satellites. And you can see some of the missions that it's flying on. The one on the SciSat is still operational, pointing Canada's first science satellite still. And you can see the technology that went into it was derived from these earlier space science missions. So we took the space science technology and developed it into a commercial product that we sold globally to lots of different missions. This next one, I don't know if many of you have heard about it, but this is Canada's only operational space defense satellite. It's called the Sapphire mission. We built the optical payload in ComDev, and you can see a picture of it there on the right, and then a schematic of the whole satellite in the middle. It's like a small satellite, close to a microsatellite. And Sapphire is basically an imager that is used to detect the position of objects in space debris, other satellites. And the data, it's actually tasked by Space Command in NORAD, which sends out a list of targets that they need to update the positions from. Because you can see here from this map, this is the number of space objects that are being tracked in Earth's orbit. There's over 25,000 pieces of debris and satellites that are being tracked by NORAD and predicting the possibility of collision with other satellites and notifying the people before it actually hits them that you might want to move their satellite if they can. So Sapphire is part of this network and serves as part of Canada's contribution to NORAD. And the data, it's given a task list of objects to look at. It looks at hundreds of these things every day, tells them exactly where they are, updates the position and the orbit calculations, which then feeds back, and every day it gets a new list. And it's been operational since 2014, and it was a 5-year lifetime requirement, so it's successfully meet that, and now it's on to its extended lifetime, and we're hoping that a follow-up mission will come soon. But this is a very sensitive instrument, very fine pointing. It's one of the recognized by the Canadian Space Agency as a signature technology, is Canada's ability to do this fine pointing and imaging of and looking at stars and positioning of sensors based on the heritage that I'm showing you here. So it's a signature technology that's been recognized by the Canadian Space Agency and is something that is known worldwide, I would say. Something that was just recently launched to the International Space Station. It's Life Sciences Research System Bioanalyzer. It's got a microfluidic chip on it which takes a drop of blood from an astronaut and puts it through a bunch of reservoirs that can fluorescently tag different proteins in the blood. And you can have as many of these chips as you want to look at different proteins. You put it in here, and this is basically includes a fluorescence imager, and it measures the concentration of these proteins. It can also has a direct cell imager where you can stain cells and image them directly as well. So there's two instruments in this little thing, and it's meant to make medical studies and life sciences studies on the International Space Station much easier. Up until now, astronauts have had to take vials of blood from their arms and then ship them down to Earth to be tested in labs for all the medical studies that they do. This would make it much easier. Now they just have a little flechette that cuts their finger and puts a drop of blood on each slide. So it's much less intrusive and much faster in terms of the results that are being achieved. And that was built by ComDev and launched to the space station. It's up there now. Now I want to get a little bit into Canada's optical space future. Many of you may recognize this. This is the James Webb Space Telescope. It's NASA's next flagship astronomy mission after the Hubble. Hubble had a much smaller mirror on the order of a couple meters. This has a 6.5 meter aperture, so it's going to get a lot more resolution. And it's aimed at looking at the infrared sky, where the red-shifted light from the first galaxies can be detected. So this is aimed at imaging the first galaxies in the universe with this huge mirror. And because of our signature technology and the recognition that we got from these previous programs in space science and commercial star trackers, NASA picked Canada to supply the fine guidance sensor for this instrument. And the fine guidance sensor instrument here also has a spectrometer on it, a near-infrared scientific instrument on the obverse. I think this is the near-infrared side. The other side is a guiding sensor, which, again, is just a big star camera. And this is basically the critical technology that stabilizes the whole telescope for NASA. So this is the key one thing that needs to work for this $10 billion instrument to actually get good data. And this was built here in Ottawa and tested over at the David Florida Labs just down the road. And we delivered that to NASA in 2012, and they announced, the most recent launch date announced is 2021. We started work on this back in the late 90s, doing studies and looking for government support to get Canada to contribute to this. So it's been a long road, and most of space science is a long road like that. So 2021 is the launch date for the JWST, and I don't know if any of you have seen this, but this is an XKCD comic which plots the announced launch date versus the current date and does an extrapolation. So the good news is the slope is less than 1, and it should launch sometime. So based on the expertise that's been generated in Canada on this program, this is built at room temperature, these optics, and they operate in space passively cooled at between 40 and 50 Kelvin. So that's like minus 100, minus a couple hundred degrees. So it's amazing that you can get an optic that you can build in the lab and then have it work at that temperature and be so stable to finally distinguish the stars and provide feedback to the guidance computer on the spacecraft. So based on this expertise, Canadian astronomers have wanted to move on and push forward into new frontiers for Canadian astronomy. And so the next thing I'm going to show you is an animation of a study that we've done for the Canadian Space Agency in collaboration with the Canadian astronomical community for a next generation Canadian-led space telescope. Now hopefully this works.
For nearly 30 years, the Hubble Space Telescope has dazzled both scientists and the public with breathtaking images of planets, nebulae, stars, galaxies, and the distant universe. But as Hubble nears the end of its mission, such images will no longer be within reach. Castor is a Canadian concept for an innovative space telescope that will not simply continue, but surpass Hubble's legacy of discovery at a fraction of the cost. Castor's compact, low-mass design will deliver images of the cosmos in 3 separate channels, ultraviolet, blue, and green, simultaneously. These images will be nearly as sharp as Hubble's, but cover an area 100 times larger. During its 5-year mission, Castor will map 1/5 of the entire sky, measure the 3-dimensional structure of the cosmos, and address one of the greatest mysteries of modern astrophysics, the nature of dark energy. It will record bursts of energy produced as black holes accrete stars and gas at the center of galaxies, all the way from the furthest reaches of the universe, and help understand how black holes form and evolve. Closer to home, Castor will point to the sources of gravitational waves and unlock their mysteries by dispersing the ultraviolet light from merging and exploding neutron stars. Peering through the remote outskirts of our Milky Way, Castor will explore the nature of dark matter by searching for the predicted population of faint and elusive satellite galaxies. By monitoring the brightness of stars with orbiting planets, Castor will probe the composition of the planet's atmosphere and assess their suitability for life. Finally, Castor will produce a census of objects in our own solar system, including dwarf planets beyond the orbit of Pluto. Undetectable from the ground, these dwarf planets will be revealed as faint sources that move between exposures. Images collected with Castor's gigantic billion-pixel camera will be transmitted to the ground, where they will be analyzed by scientists and made available to the public. Castor is being developed by Canadian astronomers and engineers, with support from the Canadian Space Agency, Canada's high-tech space industry, and Canadian scientists have long played important roles on major international space astronomy missions. As Canada's first flagship space astronomy mission, Castor will build on this history of success, providing the public with a demonstration of Canadian prowess in the competitive high-tech field of space astronomy, while opening new windows on the cosmos.
So that was Castor. I should make a caveat that is not yet funded to go ahead. The Canadian government has recently announced a large robotic arm development, which may delay the start of that project. We're not sure. This next one, though, has been announced by the government and is funded. This is KeySat. It's a quantum key distribution optical satellite. And this is planned to be launched in 2021, and Honeywell was awarded the contract by the Canadian Space Agency to build this satellite. And what it's going to do, it's a prototype that distributes unbreakable cryptographic keys between remote users. So it's part of the quantum entanglement, exploiting the weird connections between quantum mechanically entangled photons to use physics to provide unbreakable cryptographic keys. Now, this is currently being done through terrestrial fiber optics. People can distribute single entangled photons between 2 users using fiber optics. But because the fiber optics absorb ever so slightly, you can't really go much more than about 100 kilometers before the photons just don't get through the fibers. And that's why you have to have typically more than one photon in your communication system. But you can get around this by using space. Space is not an absorptive medium, so once the photon gets through the atmosphere, it goes unimpeded up into space, and all you have to do is hit a satellite with it. Now, that is more difficult than it sounds, but it's very similar to the sort of pointing accuracy that we're used to building with the James Webb Space Telescope and our star trackers and all of our other technology that I'm going to be talking to you later. So we believe that this is definitely a feasible technology, and in fact, the Chinese have set up a satellite that has demonstrated some of this. We're hoping to also do some quantum mechanical experiments with this. And you can see here on the right is a telescope that we built in collaboration with the Space Agency and the Institut National d'Optique in Quebec for the KeySat mission. It's a 26 centimeter aperture, centrally obscured telescope. And we're right now working on developing the detailed design for this mission. So now I want to switch gears a little bit. I've shown how space science has been a key thing here, and optics have been a key part of Canada's heritage in space. Space science is enabled by space communications and by the space launchers, which are all enabled by commerce. Canada doesn't rely on its civil budget for its space activities. Canada is mostly driven by communications. And that makes sense because Canada is a big company. In fact, much of what Canada does in space is to address the needs of Canada. So you can see here I've put a selection of Canada's leading space companies. Maxar, which was MDA until recently, runs the RadarSat constellations, which are very good for mapping of territory and emergency management, flood mapping, that sort of thing. Honeywell, which was ComDev, the communications to link the country. ExactEarth, which was the spin-off of ComDev, which monitors shipping traffic. And Telesat, which is Canada's only domestic communication satellite operator, also here in Ottawa. So this forms the backbone of Canada's commercial space. And if you break it down by sector, you can see that communications is by far and away the biggest driver of space. And in fact, the Canadian SATCOM market, including terrestrial spin-off revenues, was $4.7 billion in 2017. And roughly half of that was broadcast television from satellites. And you can see the other smaller portions of it. Earth observation, of course, does have commercial applications, navigation, GPS, that sort of thing. I want to give you a kind of a backgrounder here on high throughput RF communication satellites, which are driving this market of communications, or which have been driving it up till now. So this is kind of a little schematic showing you the applications of satellite communications. Obviously direct broadcast television, but satellite phones, internet over satellite, and up on the upper, on the top there you have a schematic of a GEO satellite. Now GEO means geosynchronous Earth orbiting. So we put these satellites up in a particular slot where they orbit in sync with the Earth so that they basically hover over a point on the equator and orbit at the same rate that the Earth spins. And that allows you to set up your dish on your house and point it in one spot and not have it move, because these satellites are orbiting at a fixed speed, at the same speed that the Earth is rotating. And what they have is they have a network operations center somewhere that's beaming up the data to the satellite, and the satellites have something like 10 to 20 meter antennas which detect the Ka or Ku band uplinks, roughly about 1.5 gigahertz of bandwidth that you can put through a single through that band. And these things are operating around 26 or 20 gigahertz frequency RF. These is then detected on the satellite, filtered with narrowband filters, multiplexed into different transmitters, amplified, filtered again, frequency shifted, and put out into a pattern of spot beams on the Earth to all the users that are picking it up. And these spot beams are offset in frequency and polarization so that they don't interfere with each other. And similarly, satellites have to be spaced out by about 2 degrees in longitude so that the uplink beams don't interfere with each other. So you're limited in the number of geosatellites that you can have due to electromagnetic interference, and these are all limited by by the spectrum available to you at these frequencies. They have to buy spectrum from a global clearinghouse that monitors and hands this out so people aren't stepping on each other's toes. And you're limited to about a gigabit per second per transponder. And other things you have to think about. If you're in geosynchronous orbit, it's 36,000 plus kilometers altitude. And so just the time of flight for the signals at the speed of light is about a quarter of a second. So think about having internet through a geosynchronous satellite with a quarter of a second delay going back and forth. It's longer than any of the transoceanic terrestrial fibers, which are in the order of 5 to 10,000 kilometers only. So there's some drawbacks to using this, some advantages as well. The satellites themselves are like the size of buses. They're 6 or 7 tons, and they have power supplies, huge solar arrays generating 10 kilowatts, 15 kilowatts of power to power all of these transponders. So it's power hungry, it's expensive to buy the spectrum, and that's one of the reasons, or several of the reasons, that we look at optical as the next thing. We know on Earth we've gone from RF to optical for most of our communications needs. And the same sort of evolution is now happening in space. And it's just delayed because space is a difficult environment and it takes a while before you can make sure things will work up there. So space is a little bit behind the 8 ball. And they don't want to introduce new technologies and risk these billion-dollar satellites failing with, nobody wants to be the first one to fly a new technology on these satellites, especially not the insurance houses. They don't want that at all. Because these have to last for 15 years, basically. That's the typical. It's about as far as you can push them before they become too expensive to actually build. The radiation will kill them after that. So here's another thing to note. The long-term trend in geosatellite orders is collapsing. And the main driver for this collapse is the satellite-based broadcasting market. People aren't watching as much TV as they used to. People are watching streaming internet. So as that drops off, the geosatellite market has also dropped off. And you can see here in 2002, that was the photonics bubble bursting. So nobody wanted to buy anything at that point, recession. And people started to think in 2016, as the things were starting to drop, maybe it's just the 15-year life cycle, but they haven't come back to the historical levels, and we think it's because of this change in the market. And in fact, one should note that Honeywell bought ComDev in about 2016, and things went downhill after that. So thus, our presence here as the optical technology center of excellence to develop the next big thing in communications market. So, space-based optical comms, is it a disruptive breakthrough? It has a long history. We've been working on the technologies behind this since the late 90s. And in fact, a lot of the basic technologies were feasible back in the late 90s to do optical intersatellite links, communication links between satellites, but the market wasn't there. Nobody really needed it, and nobody wanted to make the big investments necessary to put together the systems that would work. And they were expensive too, cutting edge technologies. What are the benefits? So on the right I have a kind of a schematic of what you might be thinking of as an optical network. And you have satellites up there, the red lines are optical, the blue lines are RF down to users. So you have backbones of high data rate in optical, which then allow distributed RF to users. Optics gives you satellite hardware that's smaller, lighter, cheaper, and consumes less power than the RF hardware because the beams are more concentrated. They're also more private in that way. They're more secure. You have no ITU spectrum purchasing issues. You don't have to purchase laser wavelength because you're not going to contaminate your neighbors with a laser. You can support high-resolution Earth-observing satellites that have these huge cameras generating gigabytes of data, but no way to get them down on RF. These satellites can be imaging all the time, generating huge swaths of data, but it's the pipeline from there to the ground using RF that limits their use. broadband internet services to remote rural locations all around the world, access to airplanes and cruise ships, potentially. These are all of the drivers. It also has a disruptive effect on astronomy. This is, on the right, an astronomical image from an astronomical telescope that was observing shortly after Elon Musk launched his first 60 Starlink satellites. And you can see them streaking through the image, basically destroying the astronomy. Thousands of satellites are being planned by these entrepreneurs. The Starlink satellite, as of November, SpaceX has deployed 122 satellites. They deploy basically 60 per launch, and they're expecting 2 more launches this year. In total, they want to launch 12,000 satellites into low Earth orbit by the mid-2020s to supply this global broadband internet, with a possible extension later to 42,000 satellites. And the reason you need a lot of satellites is because they're in low orbit. The geosynchronous satellites can look at the whole globe. These satellites are only 500 kilometers up, so they have a much smaller footprint per satellite, which means that you have to link the backbone between these satellites to take the data from place to place. But they're closer, so that means they have lower latency. So you can have internet through these satellites with no latency, or no worse latency than going through suboceanic fiber. So Elon Musk has said that he will try to paint the next ones black, so they won't have such an effect. But I don't think that's going to have a big difference in terms of the astronomical impact. These are very bright. So, despite that fact, there are good reasons to push ahead with this and address these issues. Canada is a world leader in the telecom markets and has historically been a world leader. Anik A1 is the world's first domestic communications satellite for Canada. As again I've mentioned, the ComDev RF switches are nearly universal. And then the terrestrial communications market, Ottawa and Canada have led the way. You're all familiar with that history. We are really in a good position right now to lead the evolution of space-based communications from RF to optical. And I'm hoping that this does come to pass. But to do this, there's a challenge. We have to hit another spacecraft about 6,000 kilometers away while orbiting at 7 kilometers per second, and communicating then by laser at 10 gigabits per second, which is not really a blazing speed, but the link losses are huge because you're 6,000 kilometers away and you have to, the beam will spread out over that distance. Even though it's a laser, it still diffracts outwards. So the accuracy requirement of this, to get the sort of power levels that you need, is kind of akin to hitting somebody walking a kilometer away in the eye with a laser. That's the same scale that this system will hit. And when you do that, you have 75 decibels of link loss. And anyone who works in photonics communications knows that that's above and beyond what you typically get for these undersea fibers. So you need state-of-the-art detectors, amplifiers, very clean systems. And we started working on this. We've been working on this for a couple of years now, back for Honeywell now. And it brought to mind a movie that I watched back in the 80s. I don't know if anyone remembers the Real Genius movie starring Val Kilmer, where Val was working in the lab developing high-powered lasers as a student. It was really cool. I thought, oh wow, I'm like Val Kilmer here. We're developing this. And someone else is developing a pointing mirror in the other lab, and it's like, geez, we're doing that too. This is great. But then I remember that the whole point of the movie was that they sold it to a big multinational defense corporation to destroy houses. We're not doing that. Cross my heart. And you couldn't do that with our lasers. So the challenge. Constellations of, now there are different constellations out there. Obviously Elon Musk is going for the big shock value of thousands of satellites. Telesat Canada is also trying to develop an internet satellite constellation with hundreds of satellites, much more reasonable numbers. But to close the business case and to make this competitive with existing communications, they need to build hundreds of satellites at a total cost per satellite of less than $10 million each, on that order, to compete for the internet market. Now, there are existing optical space terminals, and I've got a picture of one there from Germany. This is an optical intersatellite link terminal that has operated in space and has been demonstrated, but it costs $20 million per terminal. So the two don't meet right now. And that's the work that we've been doing the last couple of years, is to trying to get this down. So what are the challenges, the finer challenges? Let's break it down. So you need to isolate your transmit from your receive by more than your link losses. So you need about 85 decibels of isolation between your high power transmit laser and your high sensitivity receiver, and you're sharing an optical chain. So you need to isolate, you need good filters. Tiny vibrations in the satellite itself will jitter the beam by kilometers at the other end. These satellites are stabilized using rotation wheels that are rotating at tens of hertz, big heavy flywheels that they use. They put brakes on it and they use that to point the satellite in 3 dimensions. If there's any jitter in those bearings, on the order of hundreds of microrads is not uncommon, and you're pointing a 10 microrad beam at a satellite 6,000 kilometers away, you're going to be wobbling all over the place. So the difficult part of this is to have an active vibration cancellation system that stabilizes the beam to the sort of level of a fraction of its beam width. Tiny thermal distortions will cause your pointing of your satellite laser to be different than what you think it is. So if you have a thermal gradient in your telescope on the order of a few degrees, you're no longer hitting the satellite. So the thermal management issue is huge, and that's why Elon Musk isn't going to paint his satellites black, by the way. Because you need to not be just absorbing all the sunlight that hits you, because these things are coming in and out of the clips as they go around, and they're just going to go all over the place. Elon Musk's satellites don't have optical links on them yet. He hopes to have them by the end of 2020, he said. But he also has to solve these problems. And I think we're ahead. The systems need to last roughly at least 10 years to close the business case in a good fashion in a harsh radiation environment. The trade-off is the higher up you go, the closer you get to the Van Allen radiation belts. Now, the Earth is surrounded by these magnetic fields which trap radiation from the sun and accelerate it. And once you get up above about 700, 800, 1,000 kilometers, your spacecraft is starting to enter these radiation belts, and it quickly degrades the electronics and kills the system. But the higher you get up, the more coverage you have. And the less satellites you need in your constellation. So it's a difficult trade. You need less satellites, but you need them to last in a harsher environment as you go up. The other thing is the space debris issue. Anything below about 600 kilometers will degrade through atmospheric drag over, say, a 10 to 20 year period and re-enter the atmosphere. So it won't be up there forever. Anything above about 650 kilometers could be up for centuries. And there's a big problem right now with space debris, as I showed you previously. And if you're launching thousands of satellites into these orbits above 600 kilometers, where they could stay for hundreds of years, then you've definitely got a problem, because it's going to rapidly devolve into accelerating debris problem. There's no way you can avoid a bullet coming at you at 14 kilometers per second in time to move out of the way. In fact, satellites previously have maneuvered into each other's way by accident, not realizing that their station-keeping maneuver is actually in the path of another satellite. The good news, space is a perfect dispersion-free medium. A lot of the work that's being done in modern fiber optic telecommunications is to get over the problems of dispersion in fiber optics and how high-speed signals tend to spread out and become a big mess. In space, if you send out a sharp pulse, it comes to the 6,000 kilometers away still as a sharp pulse, no matter what the color. Space has very little dispersion. You need to go several 100,000 million light years to actually have an effect. So this is the one good note. Luckily, Ottawa has the tools to address this problem. R&D center here for global optical internet providers, major center of dominant SATCOM RF components, that's us, and also home of Canada's signature space optics capabilities, honed on space astronomy and the science missions that I've shown you. Home of Telesat, Canada's only domestic satellite communication operator. A government commitment to bring high-speed internet to rural areas. So there is funding available for these initiatives from the government, and we've made use of funding through the Canadian Space Agency to develop our prototypes to where they are now. So what are the enabling technologies that we need to make this happen? And you can see that things are improving. There are Moore's laws that are helping us to get to the point where we can do this. High quality single point diamond turned aluminum mirrors are now at the point where they can be used straight off the lathe with the right surface finish to do the job in the infrared, in the 1.5 micron communications region. You can see on the bottom right there, the high precision diamond turning was approaching 10 nanometers in surface roughness in the year 2000. You need to be below 10 nanometers to get the sort of surface finish you need for these wavelengths. And we're at that point now. So we can take these things right off the lathe and assemble them quickly in a modular fashion. High power semiconductor lasers have been accelerating up a Moore's law curve, and the power efficiency has also been improving. Power is a very limited resource in space, and we need relatively high powers to bridge these gaps. 10 plus gigabit per second optical transceivers are available now. They weren't available back 10 years ago, 20 years ago when we first looked at this. Radiation tolerant control electronics and detectors, that's something that is continually advancing, the electronics capabilities in the radiation tolerant platforms that are needed for space. And reliable pointing mirrors and bearings. Honeywell, you may not know, is the leading supplier of momentum wheels to satellites. So we build these wheels, these flywheels that point the satellites with low vibration that is needed for the optical links. So we have these bearings as part of the Honeywell US manufacturing capabilities that we can bring into this terminal for the pointing mirrors and the low jitter optics that are needed to track satellites moving at 7 kilometers per second. And here finally is our current optical link terminal design. You can see there's a coarse pointing assembly on top with a big mirror. It mounts onto a satellite body plate, and below that there's a three mirror anastigmat, which is a type of telescope, a lightweight telescope design, compact. And then we have our OpTrack on the side, which is an optical pointing terminal relay assembly for communications. The modular design, we've worked hard to make all the pieces modular so that they can be produced at the rates necessary to support the emerging constellation market and tested independently and then assembled quickly. If you're looking at hundreds of these satellites and you want to get your constellation up over the course of a year or two, you need to be building multiple satellites per year, and each satellite has, say, 4 terminals on it. So the rates of production that we need to achieve at these low price points are unheralded. But because of the scale of the operation, we can bring in automation and different production tools to the floor that help us to match the sort of production rates that are needed. And plus, we have a lot of space in Cambridge that we can actually build these in the production floors there. So you can see the scale. There's a human hand there for scale. This whole thing is about 20 kilograms, operates on 80 watts, and hits satellites 6,000 kilometers away with 10 gigabits per second of data. And just for fun, I'm going to show you some of the cool stuff that we've been doing. So this is our optical lab, and this is the breadboard of the tracking system, first generation. The ATS is the acquisition tracking sensor. There's a detector there. There's a receive fiber, a transmit fiber, a fine steering mirror, FSM, and then a partner satellite beacon simulator. And what we did was we basically oscillated the beacon. We introduced vibrations to simulate satellite vibrations. We saw if we could actually get rid of them. So this next slide shows our closed loop tracking operation meeting the requirements of the 6,000 kilometer optical link. We have an introduced oscillation in the top, and then the bottom is under feedback control at 15 kilohertz frame rate on our detector. So we know we can do it. It's just a question of can we do it for the price and at the rates necessary and have it survive long enough. So we're ongoing, we're pushing through testing of environmental impacts, radiation testing of various different systems, and we also have a view for the future. So as part of our work, we're also looking at what's the next generation after this. And I've got a project, you can see we're trying to develop an optical phased array for beam pointing without mirrors, without gimbaled mirrors. And this is basically similar to the technology they use to make those spot beams on the RF satellites, but much smaller scale, thousands of times smaller on an optical chip. So what you do is you introduce a laser beam, you split it up, you phase shift the different components of it and bring them together in a small array, which you can then electronically steer your laser beam and hopefully use that to cancel the vibrations of the satellite without having to pay for a gimbaled mirror system. And this is being funded by the Canadian Space Agency under their space technology development projects right now. And we're collaborating with a lot of the leaders in the field in Canada, especially the NRC here in Ottawa, and several different universities in Ontario. And I want to leave you with one final animation. This was one that we developed also for the Canadian Space Agency at the start of this project, looking at the potential applications for optical communications in space exploration. There's no audio on it, but there are subtitles, so feel free to read along. Thank you all for your attention.